Hello, everybody. My name is Hasanpour. I'm a graduate research assistant from the University of Nevada, Reno. Today, I'll be talking about Tsunami-Borne debris loading of bridges. The participants in this project are Dr. Bakel, Dr. Istrati, Dr. Michael Scott from the OSU, Dr. Papachristos, and the HPC expert, Mr. Newell from the University of Nevada, Reno. This project is sponsored by Pierre, and its sponsorship is gratefully acknowledged. During this presentation, I'll talk about the objectives, background, and the progresses that we've made to date. The objectives for our project are to understand the twofold effect of debris, including impact and damage, and to decipher the debris wave interaction during the debris transport and debris wave bridge interaction during the tsunami inundation, to calibrate numerical methods, including mesh-based, particle-based, and hybrid particle mesh-based, to explore countermeasures to minimize debris impact loss, and to develop experimentally validated equation for use in design guidelines developed by Pierre. In general, the problem related to debris can be categorized in 4 parts. The debris transport before it impacts the structure, debris impact, which is a short duration phase, debris accumulation, and debris damming load, which is a long duration phase. The main goals of this research study are the debris transport and debris impact force on coastal structures. Debris transport involves significant uncertainties which affect the debris trajectory, velocity, impact force. Therefore, predictive equations may need to be probabilistic based. In this research study, we use a smoothed particle hydrodynamics to model the debris transport and impact on coastal structures. This method was originally invented for solving the astrophysical problems, and in early 1990 was applied to general fluid dynamic problems. In general, the SPH is a Lagrangian meshless technique in which we replace the continuum of a fluid with a set of non-connected particles. Each particle carries individual material properties such as velocity, density, mass, and interacts with other particles via sets of governing equations derived from Navier-Stokes. SPH formulation has 2 key steps. The first one is the kernel smoothing function, which means that any particle quantity is approximated using the kernel smoothing function. W is the smoothing function, which determines the range of computation with other particles, and H is the smoothing length, which determines the influence volume of the smoothing function. The next major part is the particle approximation, which enables the system to be represented by a set of finite number of particles which occupies individual spaces. These are the equation of motion for fluid in SPH formulation. The first one is the particle density, particle velocity, internal energy, and the strain. This term called the artificial viscosity. It prevents, more specifically in case of wave structure interaction, the non-physical penetration of particles when they get close to each other. To validate the SPH solver and couple SPH finite element method in LS-DYNA, we conducted 2 validation studies. The first one was related to the fluid impact on structures. The goal of this validation was to evaluate the ability of the SPH solver to predict the interaction between the fluid and the finite element part. This experiment was conducted by Klicksman at 2005. It was a 3D dam break problem with dimension of 3.22 meters in length, 1 meter in width and height. Inside the tank, a box was placed to be a representative of a shipping container, and the right part of the tank was separated by a sliding door, holding back a fixed volume of water with depth of 0.55 meters. To measure the free surface, 4 vertical height probes were installed along the tank, and the box itself was covered with 8 pressure sensors. This figure shows the applied pressure against time on the offshore face of the structure at 4 locations, namely P1 up to P4. In these figures, the blue curve shows the numerical result and the black curve presents the experimental data. As you can see here, good agreement both in terms of the maximum value and overall trend is observed. As expected, since the box is impacted by higher level of velocity, we see a high magnitude short duration phase. And I have to add that since P4 is located close to the edge of the box, it is hard to capture the applied pressure on this location. And these sets of figures show the pressure time histories on the top face of the box, namely at P5 up to P8. As you can see, promising agreements are observed here, which raise our confidence in the capability of the software to capture the interaction between the finite element, such as box here, and the fluid part. The previous validation study was the simple one. As I mentioned, the goal of that is to evaluate the interaction between the finite element part and the fluid particles. However, the main goal of our research is to evaluate the debris transport and impact on coastal structure. And we came up with this research study in the literature, which was done by Co at 2013 at large wave volume at Oregon State University. I have to mention that the majority of experimental data were collected from the DesignServe platform, which were updated by Co and Cox at 2012. In this research study, the coastal structure was represented by a column located between bays 17 and 18, and a 1:5 scale model of a container was used as the floating debris, as you can see here. To measure the free surface and fluid velocity, several wave gauges and ADVs were installed along the flume. Using the finite element for the wave maker, floating debris, coastal structure, and the flume, and the particles for the fluid, we developed a two-dimensional numerical model of the experimental setup. I have to add that in the real experiment, the debris was just allowed to move in the vertical and horizontal direction, and it didn't have any translational movement across the flume width, which made it possible for us to develop a two-dimensional model. And we check the effects of particle size and the finite element mesh size and the accuracy of the numerical model and computational runtime. And we came up with the initial particle size of 1 centimeter for the fluid and 1 centimeter mesh size for the finite element part. And the other point that I need to mention is that in the real experiment, no significant deformation of the debris was reported during the debris transport and debris structure interaction. Therefore, we treated the debris as a rigid bodies. Since this was a 2D simulation, several calculations were needed to ensure the compatibility with the experimental setup. First, the debris thickness and density were adjusted to satisfy the required draft. Then we assumed that the debris mass to column mass is identical in both numerical and experimental setup. Column density was calculated. And at the end, we needed several contacts to define the interaction between the fluid particles and the finite element parts, such as the fluid and the floating debris, and the finite element parts with each other, such as the floating debris and column. To define the interaction between the fluid and solid bodies, we use the node to solid contact, which is a master-slave penalty-based contact, and to define the interaction between the solid bodies with each other, we use the two-way segmented base contact, which is a surface-to-surface contact. Our final numerical model consisted of about 15K shell elements and 1.2 million SPH particles. To qualify the accuracy of the SPH solver and couple SPH finite element method in LS-Reno, the free surface and fluid velocity time histories at two different distances from the wave maker were compared with the experimental results. The first probe points are located at the end of the horizontal part, wave gauge number 1 and ADV number 1, with horizontal distance of about 25 meters from the wave maker and elevation of 1.25 meter for ADV number 1. The second probe points are located along the slope part with horizontal distance of about 36 meters and elevation of 1.24 for the wave for the ADVs. In these figures, the top figure shows the free surface against time, and the lower figure shows the time history for the fluid velocities at these two locations. The blue curves show all trials from the experimental data, and the black curves show the numerical results. Promising agreements, both in terms of the maximum values and temporal evaluation, were achieved. In addition to evaluate the time history of free surface and fluid velocities, we made a comparison between the numerically predicted maximum bore height at these two locations, the top figures, and numerically predicted maximum fluid velocities at ADV number 1 and ADV number 2. In these figures, the black line show the numerical results and the blue stars present the experimental data. As you can see, promising agreement between the numerical and experimental results are achieved, and the deviation from the maximum bore height at ADV number 1 from the average value of the experimental data range between 6 up to 13%, and in case of wave gauge number 2, this deviation range between 4 up to 15%. In terms of the maximum fluid velocity, the deviation from the average value of the experimental result at ADV number 1, the difference range between 2 up to 5%, and at ADV number 2 range between 6 and 22%. The encouraging thing is that this solver is able to predict the relative increase of free surface and fluid velocity as the wave propagates along the slope parts and undergoes a nonlinear transformation during the shoaling process, which indicates the ability of the software to capture the interaction between the finite element part and the fluid. Although the reasonable agreements of the free surface and fluid velocity, both in terms of the free surface and the maximum values, were observed, one of the most critical aspects for future risk assessment is the ability to predict the debris movement and transport and impact on coastal structure. To this end, we evaluated the debris velocity, nodal debris velocity, namely lower right corner and lower left corner with experimental data. In this figure, the blue curve show the experimental results, the black and red curve show the numerical data. As you can see, as the bore reaches to the location of the debris and starts propagating it, both numerical and experimental simulation give similar debris velocity. However, as the debris gets close to the location of the column, it seems that in the numerical simulation, the debris accelerate more and reaches to a higher level of velocity. This trend could be attributed to the two-dimensional nature of the numerical simulation. In numerical simulation, the applied force from the bore on offshore face of the debris are uniform across the width of the debris. However, in real experiment, it is expected that the applied pressure on offshore face of the debris and along the bottom face should be smaller at location closer to the side walls. I mean that the 3D effects dissipate some of the relief and dissipate some of the pressures. In terms of the impact force, the results of two different tsunami flow are presented here. The black curves show the numerical results and the blue curve show the all trials of the experimental data, and reasonable agreement both in terms of the maximum value and overall trends were achieved. And at the end, we made a comparison between the maximum values of the impact force from the numerical simulation and average value from all trials of the experimental data. As you can see, good agreement in terms of the maximum values is observed as well, and the deviation from the experimental data range between 14 up to 25%.
And it's about 2 minutes or so left.
Oh, yeah. Okay. After we did these validation studies and have this confidence in the solver, which gave us acceptable accuracy, we started to design our experiments at the UNR flume. This volume is a teaching volume at the University of Nevada, Reno. One of the goals of this project is to upgrade this volume and make it ready to conduct the tsunami test. The length of this volume is 25 meters, and we are considering to evaluate a range of reservoir between 10 up to 12 meters, a wide range of reservoir depth between 40 up to 60 centimeters. The downstream water level could be between 0 up to 25 centimeters. The distance between the debris and the gate between 7 and 5 meters. Based on the previous studies, the distance between debris and bridge could be between 1.2 up to 3.5 meters. And we considering to have bridge elevation between 0.2 up to 35 meters. For the gate and the opening mechanism, we are reviewing the available option. There are two common options, the sluice gate and the swing gate. We develop a three-dimensional numerical model of these options. I have to add that due to limited computational runtime, we just simulate a portion of the volume width, and it's not we didn't consider the whole volume width. The first animation showed the sluice gate, where the gate moves vertically, and the lower animation showed the swing gate, where the gate moves in the radial direction due to the hydrostatic pressure. This is still under investigation, and we are reviewing the advantages and disadvantages of these options. And at the end, as we started to simulate this phenomena, we are getting insight into the complexity of debris-wave interaction. As you can see here, I am presenting two different scenarios. The first one, as you can see, where the debris moves toward the location of the column, it has started rotating and impact the column. And we have a non-normal impact angle, which leads to non-uniform impact. And in this scenario, as you can see, the debris got trapped behind the bridge.
And
however,
unfortunately, we ran out of time. If you can wrap up.
Yeah, this is the last slide. This is an ongoing research project, and hopefully we will be able to address the questions related to the debris bridge interaction. And thank you for your time and attention.